section 10.2, path independence of line integrals. Okay, so you just learned how to calculate the line integrals. Okay, for scalar field and vector field, right? And the path generally, the line integral must be depend on the vector field or function, right? Scalar function, and starting point A and B of the path, and the path itself. Okay, so it's a very complicated. It could be a very complicated process, right? The integration depends on 4 elements. Okay, many elements can be complicated, right? It's hard, so calculation would be hard, right? So we can conclude that it will be convenient if the integral is path independent. If this one we cannot eliminate, right? Starting point and ending point, that's inevitable. It should be there, right? And f, this is a function, so we cannot eliminate, right? But the last one, the path itself, if we eliminate that effect of path out of the calculation, it will be much easier, right? Convenient to be, so we call it path independent. Okay? So it's like that. So starting from here from A to B, if it is a path independent, the integration of this path, integration of that path, integration of that path, integration of that path are the same. That's what path independence is. Okay? From A to B, you do the line integration, right? Line integral, and the values are all the same. Then it is said to be this domain D is path independence. Okay? And if it's a path independent, the line integral, okay, this is in component form, is this. This is ending point, right? This is start. So function of ending point minus some function of starting point is the value of this integration. You don't have to integrate this over. Okay? And that f, the small f is potential function, we call it. And then the calculation would be very easy, right? Just having calculation of this. To be true that, we have 3 conditions, or 3 kinds of path independent condition there. The first one is, if and only if the vector field f is conservative. What is conservative? Conservative is something is preserved. Okay, we don't lose something. We don't lose it. It's all kept. That's conservative. Okay, I'm going to explain more. I'm going to explain this each one, okay, later. But if the vector field f is conservative, then it's path independent. Then this calculation is true. And second one, if and only if integration around closed curve is 0, then it's path independent, and this is true. The third one is if the vector field f is exact, then it's path independent, and that's true. I'm going to explain each one. Okay. The first one, it is the line integral is path independent if f is conservative. What is conservative? The mathematical definition of conservative is this: gradient of scalar function f is vector field. In turn, you could easily interpret this by del f is df over dx, df over dy. Okay, I'm going to just write x and y only, and f is f1 and f2 right? So if this is true, then df over dx is f1, df over dy is f2. Then we say it's conservative. Okay? So that's the mathematical definition of conservative. Okay? If the gradient is the vector field, then it is conservative. Then we say it is path independent. Okay? And the function f, the small f, the scalar function is called potential of potential of function of f. Okay? That's the first, definition of path independence. Proof is easy. So you integrate. Let me just write second two dimension only. Dx plus f2 dy. Okay? We could do the same thing for 3 dimension, but for simplicity, I'm just writing 2D. Okay? Then it's df over dx plus df over dy. Okay? And we know that this is exact. I'm gonna, explain it later more, but actually this is, exact. If this one is true. Okay? And then that's from A to B. You can substitute with time. Dx over dt plus df over dy, dy over dt, and dt. Right? But then this is what? Actually, this is exact. Sorry. So this is exact. Okay, so what you do is this: A to B, df over dt. Okay, and then that's f A to B. So f of B minus f of A. Okay? So that's the path independent when the gradient f is f, the vector field f. Okay? Okay, so I'm gonna solve an example 2 on textbook. So I is 3x squared dx, okay, and 2yz dy plus y squared dz. Okay, that's our f1, f2, and f3. All right. So we're gonna integrate from a is 0, 1, 2 to b 1, -1, and 7. Okay? Then, our assumption is del gradient f, del f is f, right? So df over dx is what? f1, right? The x component of the vector field, and that is 3x squared, right? And df over dy, which is f2, which is 2yz. df of dz is f3, that's y squared. Okay? Okay? Yeah, I just used this relationship. That's all. All right. Then I'm going to integrate the first relationship. I'm going to integrate this first integration. So with respect to, so integrate this one with respect to x. Okay? Then f will be x cubed plus g of y comma z. Okay? If you partially differentiate with respect to x, you get this back. Okay? So you're actually getting f out of these three relationships. You're getting small f now by partially differentiating and partially integrating. Okay? And we're gonna use, we already used this one, and we need to use that one and that one, right? So we're gonna differentiate this df with dy. Okay, so it's dg of dy, because this one it vanishes, right? And this is the partial y and z, so it's a partial differentiation, and that's f2, and f2 is 2yz. Okay, and we gotta integrate this again, right? So that this one g, let me write here. So we're going to integrate it. So g is y square z plus h of z. We are introducing a new functions whenever we do the integration, right? Because it's partial differentiations, partial integrations. Okay, and then what? Then f becomes x cubed plus y square z plus h of z. Okay? All right. And we have, another one. Another condition that we need to use, right? So, we differentiate again. df over dz is here, so it cancels. It's y square plus h prime, which is here, f3, which is y square. Okay? Then from here, we know that h prime is 0, right? And integrate h will be c. Okay? Alright? Then we can choose any value for c, but we choose c to be 0. For easier, simpler, calculation. But you know why later, right? Then f of, I'm going to need another page. So f of x comma y comma z is x cubed plus y cubed and z. Okay, we just put everything all together in here. So our I is f of 1 comma minus the starting point minus 0 comma 1 comma 2, and that is 1 plus 7 minus 0 plus 2. So it's like 6. Okay? Okay, so x square plus y square dx plus 2xy dy, and c is cosine t I plus sine t j, and t is pi. This is a circle, half circle, right? 1, 1, minus 1, from 0 to here. So that's starting point, that's ending point, right? So we are, getting the line integral of that. So, so from that relationship, df over dx is x squared plus y squared. df over dy is 2xy. And we have to integrate this one first, right? F of x comma y is x cubed over 3 plus x y square. So it's integrating with respect to x, right? And we have a known function g, function of y. So we have to differentiate this with respect to y. So it's say 2xy, right? You differentiate this, and that's g prime, right? Then that's this one, right? df dy, so 2xy. So here g prime is 0, same thing. G is c, and we take c to be 0. Okay? And so f of x comma y will be x cubed over 3 plus xy squared. Right? And since the starting point for the x, y, so it's so the integral of f dot dr, let me write for easier writing, minus 1 0 minus 1 0, so it's minus 2 over 3. The second one is, it is path independent if and only if integration around closed curve gives 0. This is quite obvious in some respect, that it starts from A to B and it moves like that. The path is, this one is plus, right? And from this respect, this is starting from is this and ending point is this, right? So you could say that this is minus, not 1. You could say that this is minus negative, way of rounding it from starting to end, right? So it becomes 0, and that integration is 0, then it is path independent. Okay? You could see the proof on the textbook. I'm not going to do it here. And second one is kind of we don't have much application for second, right? And work in that respect, work is conservative because it is path independent. You could always find the gradient function of a potential, and it's conservative. But if there is a dissipative forces such as friction, resistance, and it may be a non-conservative. The third one, all right? So it is path independent. The line integral is path independent if and only if f is exact, and that is curl f is 0. Do you recall that? Exactness? Do you recall from chapter 2? Exactness? Right? If this kind of differential equation is given, right? If that's true, dm over dy equal dn over dx, then it is exact, right? And we can solve it. It's separable, right? Then it's separable, so we can solve it, right? So curl 0, this is exact condition, and that's exactly the third case. Okay, this is a full generalization of these two value things into 3 dimension, three variables case, and the last one is the first x and y case. Right? So this is the checking condition. If you check this, and if that's true, this one's true, then it is exact, and we could always find function f, potential f. We have this integration problem, okay, 2xy c square dx plus x square c square plus c cosine yz dy plus 2x square y c plus y cosine yz dz. Okay? So that's the integration. This is very complicated function, right? Function vector field. And we are not sure if we can find f, right? So that exact condition really gives, to make sure that we can always find that if it is exact. Let's see. So from A is 0, 0, 1 to B is 1, comma, pi over 4 and 2. Okay? So, what is it? So from the curve condition, df3 over dy is df2 over dz. Okay, that's the first condition. Okay, first checking condition, and this is 2x squared z plus cosine yz minus yz. Oops. Yz sine yz. That is, this is df2 over dz. And from the, condition df1 dz equal df3 over dz, dx, that has to be the same, okay? And that's 4xy z. I'm just writing, those are the same with respect to this, okay? And df3 over df2 over d, is it x, is df1 over dy. And they are the same with these terms, okay? And so we verified those are exact, okay? And so now we can get f all the time. So we don't have to, spend, time to not to know to get f, but this is, checking condition before we, proceed, okay? All right, and I is, we are doing the same thing, is let's see, f2 dy, okay? So x squared z squared plus c cosine yz dy. And you get, same process. This is a little bit, complicated because the function is complicated, but g of x comma z, like that. Okay? Yeah, I'm going to skip the rest, and you can practice on your own. I'm going to give you another example problem. So it's from 4, 0, 6, 1, e to the 4y times 2x dx plus 4x squared dy. So you check the condition, right? df2 over dx is df1. If it is an exact, that relationship has to be true. So let's write f1 is, let's rewrite it, e to the 4y, f2 is 4x squared e to the 4y, and df2 over dx is 8 times x e to the 4y, which is df1 over dy. It has to be, right? So it's exact. Okay? And f, we get it from here, right, by integrating it by f1 dx plus g of y, and that's 2x e to the 4y dx plus g of y. So if you integrate it, that's x squared e to the 4y plus g of y. Okay? And you have to, partially differentiate with respect to y. So it's 4x squared e to the 4y plus g prime. That is f2, and that has to be 4y, and g prime is 0. So g is 0 by c is 0. Okay? And f will be x squared e to the 4y, and the integration from 4 comma 0, 6 comma 1, e to the 4y times 2x dx plus 4x squared dy is x2 e to the 4y from 4, 0 to 6, 1, and that's 36 e to the 4 minus 16. Okay?